Let's take a look at a sample problem where we have a heavy drum of mass d and radius r, and wrapped around it is a smaller mass m1 via a rope that's connected to a spring, and the system's in equilibrium, and mass 1 is pulled downward by a small amount of delta x value and is allowed to oscillate up and down. And we're asked to find the period of oscillation. So as our drum begins to move, it's going to have an alpha. So we'll define the positive alpha to be in that direction. And as a result, this mass is going to bob up and down. So the mass is going to have an acceleration, which I'll call A1 for now. And you might be tempted to say that the tensions are the same here, but they won't be, because the drum has so much inertia, the tensions have to be different. So we'll have what I'll call a T1 here, which will be equal and opposite of T1 on the mass. And then we'll have a T2 over here, which will equal whatever force is in the spring at any given time. And to complete our free body diagram, we'd have an M1G down here. So this is what I would call a linked system. We have a linear event that's tied to a rotational event. And the crossover equations are going to be very useful here. And the crossovers are that delta L would be R d theta, V is equal to R omega, and A will equal to R alpha. And these crossover equations will allow us to link the linear information with the rotational information. If we pulled this mass down by 2 inches, then delta L would be 2 inches, and that would give us our theta value that we have up top. So really this is just the arc length formula if you think about it with respect to up here. So that's our starting point for this. So first I'll do the linear sum of the forces on mass 1 will be M1 A1, and we're going to call the direction of A the positive direction. So we have M1G minus T1 is equal to M1A1. We really don't need the 1 on the A. And we'll solve this for T1 so we can substitute it up onto the drum. So T1 will be M1G minus M1A. Next, let's think about what's happening back here with the spring. When this mass M1 was added to the system, the spring elongated by some small x0 back here. So we should do moments around the drum in order to figure out the relationship between x0 and the mass down here. So our equilibrium point, we can do sum of the moments about the drum will be 0. Whatever torque we have acting in this direction, T1, would have to equal T2 so the drum doesn't move. So that would give us M1G times R has to equal Kx0 times R, force times distance. So we have M1G acting a distance R out here, and we have the force in the spring pulling back a distance R up here, and those two have to be in equilibrium because the drum's not moving yet. That's our starting point. The R's go, and we find that M1G is equal to Kx0. So that's an equilibrium condition, which is useful because it relates the weight hanging down below M1 with our spring on top. Now let's pull the drum forward some delta X value and release it, and it'll begin to oscillate up and down over time. So we'll have some of the moments about the drum will be I drum alpha. We're going to define positive as this direction. So we have T1R minus T2R is equal to I drum alpha. So we're addressing the two tension forces. We know what T1 is, so we have M1GR minus M1AR minus T2. Now T2 is the spring, and the spring has been pulled back by Kx x0 plus delta x. So that's our spring force pulling us back, and that's times r, and that's going to equal I of the disk times alpha. Now we have an acceleration here, a linear acceleration, and an alpha over here, and they are related. A will equal r alpha since they have a common radius here that they share. And we know that m1g is kx0 also. So let's substitute that into here. So we'll get kx0r minus m1r times r alpha minus kx0r minus k delta x r equals I disk alpha. This mr squared can come to the other side with the other alpha, so we get m1r squared alpha here. We have a kxr0r and a negative kxr0r, so they're going to cancel out. So this cleans up a little bit. We have a delta x hiding here, and delta x will be r theta from the arc length formula. So if we plug all that in, we get minus k r squared theta, when we have two r's now over there, equals I of the disk plus m1r squared alpha. And I can put in what the I of the disk is, we know that. It would be 1/2 big M drum r squared. And this is interesting here. That's the I total of a drum with a concentrated mass stuck to it. So it views this mass that's hanging down here as if it was a mass fixed onto here, and it's trying to oscillate back and forth with that attached. Continuing, we know that alpha is theta double dot. We can divide through by r squared, so it's independent of the size of the drum itself. If I multiply through by a 2, just to get rid of this fraction here, and then rearrange this for theta double dot, we'll get theta double dot plus 2k on md plus 2m1. Theta is equal to 0. And with that, we recognize our characteristic equation. And we know then that that is our omega squared value. And then there's our answer. Omega will equal the square root of 2k on mass of the drum plus 2 times the small falling mass. And from there we could get t is 2 pi on omega if they wanted the natural period. And we could predict where it was in time. So theta would be theta max. And in this case, we would use cosine of omega t, where we assume it starts out here at theta max and starts to move back and forth. And we could predict its location with that. Thanks for watching.